Hello and welcome to another creative coding video. Today we're going to be taking a slower, simpler look at the new idea we introduced last time. Now last time we talked about how to move around a circle in an orbit, and we introduced a bit of mathematics from what people call trigonometry, and unfortunately people are a little bit afraid of that word. Some people don't like it. It brings back unhappy memories from school. But I hoped in the last video just to show you that a little bit of maths, which is simple, can be really useful. So let's get started. On the screen we're looking at a circle, and I am showing dots moving around this circle, evenly spaced dots, and it's often useful, in fact it's very useful, to be able to start a design with points or lines or shapes or elements that are arranged in an orbit around a circle. We don't always have to move in regular kind of rectangular or square grids. Circular designs are really interesting, really powerful, and it would be wrong if we didn't know how to do that. So what I've done here is I've kind of drawn extra things on this circle to make it look like I've taken slices out of a cake. So I've got a dot here, and then I've got a slice of a cake, and the next dot, and a slice of a cake, and the next dot. And what we want to do is to be able to think in terms of moving around a circle, either in terms of cake slices, or, a simple example is just thinking about a clock. So, 12 o'clock, 1 o'clock, 2 o'clock, 3 o'clock. That kind of thinking around moving around a kind of an orbit is natural. It's how we think about a circular kind of journey. Unfortunately, when we code, we need to describe these positions in terms of XY coordinates, in terms of their horizontal and vertical position, and those two things are different. On the one hand, we want to think about how far around a circle we've moved. That's one way of thinking about it. We've moved to 3 o'clock, say, or 6 o'clock, or we've moved 3 or 4 slices of a cake around. And the other way is XY, how far along and how far down. And converting from one to the other isn't immediately clear. How do we do that? We could have a go. Let's kind of illustrate why this isn't so simple. So let's just imagine this is the center at 0, 0. This point here to the right could be at 1, 0, 1 across and 0 up. This one here is 0 left and right and 1 up. Easy peasy. This one could be 0, minus 1 and minus 1, 0. That's easy. But what about this one here? That's kind of halfway between that one and that one on its journey around. This point here, what's the XY coordinate for that? What are the XY coordinates? Well, that's 1, 0, that's 0, 1. Is it half? No, it's not. And that's the challenge that we have to solve. And the answer is actually really easy. You just have to know it or look it up or kind of Google it. So that's the reason we're doing this video. That's the reason we're talking about this scary word trigonometry. It's just to be able to convert from how far around we've gone to XY coordinates for any point on a circle. Let's roll back a little bit, because that sounded quite deep. So let's go back and take simple steps again. So here's a point moving around a circle. How do we describe it? Well, naturally we want to think about its rotational journey, like the Earth moving around the Sun. And one key bit of information is how far away is it from this center of rotation, from this center point. and we can call that a distance d or a radius r, because that's the radius of this big circle. That describes how far away it is. The other key bit of information is how far around it's actually gone, the angle. Is it here? Is it over here? Is it over here? How far around has it gone? And a good way of describing that is the angle it's made. Now, angles are something that we come across when we were young in school. Let's see if we can find a picture to describe them. There you go. So, angles can be described in terms of degrees. You might come across something called radians, and mathematicians like working with radians because it makes their equations simpler. But for us, degrees is fine. Degrees is easy for us, we're familiar with it. Here's a picture here on the left showing 45 degrees. Here's 90 degrees, which is a quarter of a turn. This is 180 degrees, which is half a turn. So if you started facing this way and did a 180 degree turn, you'd be facing backwards. And 360 degrees is all the way around. So that's familiar to most people, and that's exactly how we're going to describe this angle in terms of degrees, how far we've moved around. Now you might notice we're starting in this position along towards the right. Some people start at the top, some people start somewhere else. As long as you're consistent, it's fine. Many people like to start over here. The important thing is that angles grow anti-clockwise, so it's an opposite of a clock. So we go around this way. So this picture is showing a point, and it's showing both ways of describing that point, x and y, or a combination of the distance and the angle. If you've got the distance and the angle, you've described where it is, or if you've got x and y, you've described where it is. Now we want to think in terms of going around a circle. We want to say it's, I don't know, 10 degrees, 20 degrees, 30 degrees, 40 degrees, or we might want to say it's 1 slice, 2 slices, 3 slices, 4 slices going around. And we want to be able to convert those into x and y. And the magic, the thing that makes it happen, is called trigonometry. It's a part of mathematics that deals with working with angles. And before I show you the answer, it's important to know that you don't need to understand where that answer came from. It's interesting if you want to know, but many people, many professionals, many algorithmic artists, many designers, many architects just use it, and that's perfectly respectable and that's fine. Most people will just use the answer without having to worry about where it came from and the history of it. So let's go and show the answer. And that's the answer. If we know the angle and we know the distance r, we can say sine of angle times r, that gives us y, the vertical coordinate. So that converts from one way of thinking about the point to the other, and the same for the x coordinate. We know the distance r, we know the angle, and we take the cosine. Now sine and cosine, they should be familiar because previously we looked at interesting mathematical functions and making sort of creative use of them, and the sine function gave us the sine wave. It's a wavy kind of function. So do go back and look at that video. I think there were 2 videos, because you kind of build a better intuition of how it works. So that's a nice connection there between those waves and sine and cosine. If you don't want to, that's alright. You can just use these formulae, these kinds of expressions. So let's put that into action. Let's get coding. So let's imagine we've got a center of orbit at the center of our canvas, and we want to move around, kind of like around a circle, all the way around, but we want to start here and move around in steps of 10 degrees. So maybe 0 degrees, 10 degrees, 20 degrees all the way up to 60 degrees, and at each point we're going to draw a dot. Should we do that? So from 0 degrees, taking sort of these pie slices as it were, all the way up to 60 degrees. Let's try and do that. Let's get coding. So I'm logged into Open Processing as usual. I've enabled my simple library, yep. And I've got simple enabled in my setup section, and I'm ready to code. So I'm counting angles from 0 to 60 in steps of 10, and that suggests the repeat instruction. So repeat keeps a loop counter, and here we're starting it at 0, going up to 60 in steps of 10, and I'm going to pass that counter to a function called spot, this one here. I have to write that function, so function spot, and it takes that information. We can call it, I don't know, M or N or A or angle. It makes sense to give it a name that makes sense. So it's an angle that we're counting. So let's work backwards from what we want to do. We want to draw a circle, a little dot, at X and Y, size 10, let's say. What is X and Y? It's exactly those mathematical expressions. So let's write them out. X was r, the distance from the centre of the orbit, times the cosine of the angle. And the vertical coordinate of y is r times the sine of the angle. That bit of code here, that's the magic, that is the core of the idea, that is trigonometry happening. Again, like I said before, you don't need to understand where it's come from, but you'll be able to spot other people using this because it's so useful. It converts from angles to xy coordinates. Now we can't run the code just yet because we haven't said what r is. Let's use lowercase r, it fits the style better. What is r? Well, it's this distance here, isn't it? How big the orbit is from the centre all the way up to the kind of the line that the orbit makes. It's how far away from that centre it is. This one here. So let's call that 200. In fact, it is 200 on this drawing. 200. Let's do that. Let's say var radius is 200. So that's 200, which means 200 times the cosine of the angle will become x. Let's run the code to see what happens. That's odd. I expected dots to be drawn around here. Why is it up there? Let's go back to our sketch. Well, we've assumed that 0, 0 is in the middle of the canvas. But we know on our canvas, in this coding language, 0, 0 is on the top left. So we need to translate, we need to shift it along 400 and subtract it from 300. We've done that many times before. It's quite easy to do. So let's do that. Let's give that a go. So we will say whatever the x was, we're actually adding 400 to it. So 400 plus x. And for y, we're subtracting it from 300. Let's see if that works. Yep, that worked. Can you see? It's 1, 2, 3, 4, 5, 6, all the way around. 0 degrees, 10, 20, 30, 40, 50, 60 degrees. And it's moving around an orbit. Fantastic, job done. I hope that little teeny bit of code and this kind of picture that it's drawn has shown you what's happening. We are counting an angle to go from 0 to 60 in steps of 10, and we're drawing a dot, a circle, a spot at xy, and we're using trigonometry, this magic here, to convert from the angle and the distance to x and y. That's the magic, and I've just shown that it works. In fact, let's count up to 180 degrees, just to prove that it does go all the way around half a circle. There you go, magic. So you can already start to see that this is a basis, a good foundation for drawing interesting designs that build on this kind of orbital movement. Let's just test it goes all the way around with 360 degrees. It does. Great. So we could stop there, but I'm gonna carry on just a little bit, just to make something interesting out of this idea. It's always nice to finish with a nice drawing. What could we do? Well, those circles have black dots around them, and do I like them? Let's keep them for now. What else could we do? What happens if we if we don't go around the circle once but twice? So we count from 0 to twice 360, which is 720. We can just type times 2, it'll do the calculation. What happens then? Well, it's the same picture because it's gone round once and gone round again, and those equations just handle the fact that it's a large angle, so an angle of 400 might be up here because it's the same as 40 degrees. What else can we try? What if we said that the distance changes? So instead of 200 it was 100. That would make, let me bring that back. This would make, hopefully, a smaller orbit. Yep. If I did it 10, that would be a tiny orbit. That's really tiny. What if we varied it with the angle? So we said it's the angle divided by 8, so that the angle goes from 0 to 360. So if I divide that angle, well, let's use map. Remember the map function, which converts from one range to another range, so we're mapping from the angle, which goes from 0 to 360, and we want it to go from 0 to, say, 200. What have we done? What have we said? We've said as the angle gets counted from 0 to 360, we want to map that range not from 0 to 360 but 0 to 200. Let's see what happens there. In fact, before we run the code, let's have a think, because it's quite educational. So before we had a distance of 200 and our first spot was there at 0 degrees, then 10 degrees, then 20 degrees, then 30 degrees, all the way around, and the distance was always maintained at 200. Now what we're saying is, nope, we're going to change that distance as well. So when the angle is 0, the distance is 0. When the angle is, say, getting bigger, that distance is also getting bigger. So it might be something like that. So as well as the angle increasing, the distance increases. Wonder what we'll get. Will we get some kind of spiral? I don't know. Let's see. Let's try it. Yep, we did. So as well as the angle increasing as these dots go around, the the distance from the center is also increasing. So that's quite nice. That creates a really nice kind of effect. And then we can play with that. We can say we'll go from, let's make it go in much smaller angle steps, and let's let's see what that does before we continue. Oh, that's quite dense there. It's quite a nice design. Let's make the circle bigger, those little spots. That's interesting. Let's make them see-through, because I think we're missing a little bit of detail there. So we'll say no stroke, no fill, sorry. Get that right. And for the stroke, yeah, well, let's see what the result there is. Okay, there's a lot of saturation there. Let's use translucency. We've done that before. It helps bring out detail when there's lots of kind of detail to be seen. So we'll use RGB 200 for kind of a red, 0, 0, and a translucency of 50. Let's see what that does. Oh wow, look at that. That's interesting. That is really cool. What if we went round more than once? So let's say 4 times around the circle. So we're going round 4 times. So let's see. Look at that. Magic. Isn't that cool? That's magic, isn't it? Look at that. So all we've done is we've moved around an orbit and we've increased the distance from the center to create this kind of nice sort of spiral effect. That's really cool. It's amazing how really simple ideas can translate into such rich kind of designs. Didn't take much, did it? Look at the code, it's tiny. So I will stop there. I know I sometimes do longer videos, but have a go yourselves. I mean, there's lots of things you can explore here. There's lots of different ideas you can kind of use to change it. I'm going to be naughty and try one, even though I said I'm going to stop. I'm just going to make the circles bigger. Wow, look at that. I'm going to try one more idea. I'm being naughty. What I'm going to do is, because there's a lot of density in the middle, I'm going to see if I can start the distance not at the center but pushed out a bit. So I'm going to say that I'm going to give that distance a minimum size. So the way I'm going to do that is simply to say, I don't know, add 100 to the radius. Just see what that does. I'm going to bring that back down to 50. Let's see what effect that has. I'm hoping it creates a bit of a hole in the center. I don't know. Let's give it a go. Yeah, that kind of does. Maybe that's too big. Maybe make that 50. So the minimum size is 50 there. And maybe I'll make these circles size 100. It's interesting. Yeah, no, I like that. That's a nice design. Fantastic. Well, I'm going to stop there. I'm just tempted to carry on, but I won't. But I hope you've seen with this simple example how using that mathematical expression, the trigonometry, to convert from a journey around a clock face, the slices of a cake, the angle, into XY coordinates, and how we can then use that to create interesting designs which have that rotational kind of journey at its core. Have an experiment yourselves, have a play. It's a really useful technique. It's kind of part of the tool set, so worth kind of persevering and experimenting and playing so it sinks in. Yeah, have fun, and see you next time. Bye.